So this first video is going to be about related rates for Unit 2, and related rates are application problems. But before we dive into those towards the end of the unit, you have to have an understanding of the product rule, quotient rule, chain rule, and your transcendental derivatives, which are your exponential, logarithmic, and trigonometric functions, okay? So if you want to just memorize the formulas, there they are. You can skip this video, but if you want a deeper understanding of how these rules work, why they work, and how they will be applied to the related rates, then this is a good video for you, okay? So for the product rule, how I'm going to explain it, it aligns with how a lot of teachers explain it, but there are a little bit of nuances that might be different. So if my way doesn't make sense to you, then get on YouTube, search visual product rule, and you'll see a ton of videos about that, okay? And they'll have nice animations and stuff as well. So it might take a couple times to understand this. If you don't get it the first time, that doesn't mean you should give up. That means, okay, let me go look somewhere else and see if someone explains it differently to where you might connect with it better, okay? And then you can also ask me in class. So the product rule is we are taking the derivative with respect to x of a product of two functions. In this case, it'll be f of x times g of x. So when you take the product of anything, you should think of area. All right, so the area of a square is side times side. The area of a rectangle is length times width, which is the visual that we'll be using for today. Okay, so I have my length and I have my width. So for this visual, we'll call f of x the width, and then we will say g of x is the length, okay? Now, basically, verbally what this is saying is that we want to look at the change in the area, okay? The derivative with respect to x of f of x times g of x is the same as saying we want to look at the change in the area, okay, of this product. So the change in the area is going to be all of this, okay? And my rectangle does not, let me fix the sides a little bit, just so we are consistent. There we go, okay, better than the last one. But the change in the area is going to be this, all right? As the area grows, we want to figure out how much is it growing. Now, this is not going to be drawn to scale because if you recall, whenever you're looking at the change or taking the change, that change horizontally should be approaching 0, okay? So technically, if you look in this bottom right-hand corner, I just drew a white dot. The change in the area of this rectangle should be even much, much, much smaller than that, all right? So this is not drawn to scale, but I am blowing it up so that we can see what we are using in order to use the effective rule, or I'm sorry, use the product rule effectively, okay? So again, it's not to scale, but it's so we can see what's going on. So the result of this is that we want the value of the purple section. So the product rule is not about seeing the original area and the change in the area. We only want to focus on the change itself, okay? That's what the d over dx represents. Now, if we start with the width, over here, as the area grows, the width is represented by f of x. That is going to be the change in f of x, which is f prime of x, okay? So as this rectangle is growing to the right, we can account for that by using f prime of x. And then the same thing as the rectangle is growing up, that's going to be the change in the length, which is the change in g, which is g prime of x, okay? So now we have some mathematical representation that represents the change in the area. So how are we going to get from here to the product rule when it's expanded like this? Well, basically what we want is we want this rectangle, because that's the change in the width, and we also want this rectangle, because that's the change in the height. I'm sorry, the change in the length, not the change in the height. We're using length and width. Okay, so if we look at this tan rectangle, that tan rectangle, the area of that rectangle, the width of it is going to be f prime of x. And then the length of that rectangle is g of x. Because if you look, here's our width, f prime of x, and then the height is going to, sorry, the length is going to be g of x. So that gives us the area of that rectangle. Now we also need the change in the length, which is going to be the rectangle sitting on the top. So if we look here, we will have the base, sorry, the width. That's going to be f of x times the length, which is g prime of x. Okay. And then hopefully some of you are wondering, okay, but what about this little rectangle here? Because that is technically part of the change in the area. Well, if we think about the area of that square, it's a square, not a rectangle, I'm sorry. It will be g prime of x times f prime of x. And if we rewrite this using Leibniz notation, this would be the derivative of g with respect to x times the derivative of f with respect to x, all right? And this is why Leibniz notation is used effectively, because you can see what you are differentiating and with respect to what. You can see it in this one as well, but being able to see it in, it's not really a fraction, but it's fractional form. We can see that technically, if we multiply these two out, the denominator will end up being dx squared. So we were already taking the derivative to where dx is approaching 0. Now it's approaching 0 twice as fast, all right, because we just multiplied it. So this square is so small that it is negligible, which means it's so small it won't change the outcome of the change in the area, which means we ignore it. Okay, so it is not part of our product rule, okay? Because again, this change here should be smaller than the point of my pen, and then that change is twice as small, so it's negligible, okay? So this is where we get the product rule, okay? It's the change in the area using the rectangle on the side, the rectangle on the top, and ignoring the square in the corner. And for memorization's sake, you will see the product rule. It could be written as g f prime plus f g prime. We always start with the first function, to where you differentiate the first, leave the second, and then keep the first and then differentiate the second. And you'll see why we do that once we get to the quotient rule. But I want to talk about the chain rule first. So an analogy that I use for the chain rule is going to be a lollipop. And I don't know what flavor this is, but so basically we'll have a lollipop, and it's going to have a wrapper and then a Tootsie Roll in the middle, okay? So for chain rule, I use this analogy because if you think of the Tootsie Roll inside the lollipop and then the lollipop is inside of the wrapper, the chain rule is used for composition functions, okay, which is a function and a function, and this can go on and on and on and on. But we are able to differentiate these using the chain rule, okay? So if I look at this, I am taking the derivative with respect to x of f of g of x. So it looks a little weird at first because, okay, well, you're differentiating with respect to x, but it's literally the furthest variable from that differentiation. But what we're saying is we are going to change x just a little bit, but that change will affect g just a little bit, and then that change will affect f just a little bit. And because the chain rule is multiplicative, we are able to see that result even though we are differentiating starting from the outside, working our way in. That change will stay consistent throughout the composition function. So what does this look like? So before you eat a lollipop, or if you've never had one, you should take the wrapper off. If you saw someone eating a lollipop with the wrapper on it, you'd probably be a little concerned, which you should be. So let's call F the wrapper, okay? So before you eat the lollipop, you need to take the wrapper off, aka differentiate f with respect to x first, okay? So I'm going to rewrite it like this. So the derivative with respect to x for f of g of x. So when I take the wrapper off, that's equivalent to differentiating f. Now when you take the wrapper off, the lollipop is still there, okay? The lollipop is going to be g of x, okay? So you took the wrapper off, You're not simultaneously taking the wrapper off and eating it at the same time. So you take the wrapper off first, and then you still have g of x there, okay? So once the wrapper is off, you have the Tootsie Roll left inside with the lollipop, okay? To get to the Tootsie Roll, you have to eat the lollipop, okay? And that's going to be g. So when you eat the lollipop, that is the metaphor for differentiating g. Now, you didn't get to the Tootsie Roll yet. The Tootsie Roll is going to be x, so x stays the same. So if you notice, I'm differentiating the outside while the inside is the same. And then I work my way in. I differentiated the outside, but the inside is still the same. Now, once you finish the lollipop, you are down to the Tootsie Roll, and that Tootsie Roll is going to be x. Now, usually, x prime, it could be a function, it could be a constant, all right? But you are technically multiplying with the derivative of x, because that's technically the last interior function. So you finally made it to the taking the derivative of x with respect to x there, okay? Now, I would say you should get comfortable with doing this 3 to 4 times. Sometimes you'll see 5 if you do the practice work, but assessment-wise in the AP exam, I don't see you ever having to do more than 4, okay? All right, so to get to the quotient rule, you have to have an understanding of the product rule and an understanding of the chain rule. There really isn't a visualizer for this because the quotient rule is just the product rule in disguise. And that's true for any time you take the quotient rule. You can technically rewrite any quotient rule to be a product rule. And I've had people ask in the past, can I just use the product rule? Technically you can, but you're going to be losing a lot of time. Learning all of these rules is about picking the one that is most beneficial for the particular problem that you are working with. So you're trying to choose the best method that works for what you're presented with. So don't rely only on the product rule. You need to rely on anything in your arsenal. The more tools you have in the toolbox, the quicker you'll be able to fix some of these problems, okay? So let's rewrite this as a product rule. So I have the derivative with respect to x for f of x times g. This will be to the negative 1x. So that's just that exponential property. So moving forward, I'm going to rewrite f of x as f and then g of x as g, all right, just to save some space, okay? So if we think back to the product rule, I'm going to take the derivative of f, so we'll have f prime, and you only take the derivative of one function at a time. We talked about that in the chain rule, right? You do one at a time. It's the same pattern with the product rule. You don't do f prime of x times g prime of x. It's f prime. Oh, there's one rule. Now you just write g. And then from here, we take the derivative of g, but we always start with f, so we'll have f prime. But that's just the normal product rule, right? So when I do g to the power of negative 1, I'm going to have f, and this will be, we'll use the power rule here, so we'll have negative 1, and then we'll have g to the negative 2, to the power of negative 2. All right, so we use the product rule, and this is technically the quotient rule here, okay? But we don't like this form because you'll still be required to do algebraic work, and then also we have that exponent that's negative, and we don't like having those in our formulas, okay? So now let's manipulate this in order to rewrite it as one term, okay? So if we keep going, I'm going to rewrite this as f prime over g. And then that negative 1, I know that looks like f of negative 1, but we're multiplying here, so I'll do it like this. I'm going to do minus f times g to the power of negative 2. Okay. So I know that's a very tiny step, but I want to make sure that we are seeing where this is coming from. So now I have f prime over g. This is going to be minus f over g squared. F over g squared. Now, I want to go back because I want to do a quick rewrite because I just taught you the chain rule and I already violated that rule, okay? So go back to here. Let's go ahead and get rid of this, and I want to rewrite it like this. So we'll do g of x to the -1. So that way, when we multiply it here, the -1 comes down. The new power is -2. This is a composition function, okay? Because right now I have the g in here, which means I did the power rule. So I did -1, and now I have to the power of -2, and now I have g in there, so I need to multiply with the derivative of that function. So that should be times g prime. Because if I look down here, if I do g of x, let's say, well, let's not use a negative exponent. Let's say g of x squared. If I want to take the derivative of this with respect to x, then that means I'll apply the power rule. So 2 times g of x, and remember, this is our interior function. The inner function is g of x, and now I'm going to multiply with the derivative of the inside function, which is g prime of x, okay? So that is where the chain rule is applying. It's that second part here where I bring the -1 to the front using the power rule, which means the degree goes down by 1, so -2. But we are taking the derivative of g of x when we do this. So we also have to multiply with the derivative of g of x. So as I come down through the steps, I should have a g prime here, which means when I put that g squared in the denominator, I should have a g prime here. All right, sorry about that. Now, in order to combine this into one term, we need to have a common denominator, so we'll have f prime over g times g over g to get that g squared denominator minus f of g prime over g squared. And if we combine them, we have f prime of g minus f g prime over g squared. And that is the quotient rule, okay? Now, if you notice, hopefully you notice, the numerator is just the product rule with a sign switch, because the product rule is f prime of g plus f g prime. So to get from the product rule to the quotient rule, you just negate the sign and then divide by g squared. So that's why we teach the product rule this way, so that it closely aligns with what the quotient rule is, because they are technically the same, just in different forms. All right, your transcendental functions, there are a few of them. So let's go ahead and start with the ones that are most commonly used. It's going to be your sine, tangent, and secant, cosine, cotangent, and cosecant, all 6 of them, okay? So if we start with sine, the derivative with respect to x of sine is going to be cosine, which if we think of the sine curve, what this is saying is that the slope at any point is going to be equal to the output for cosine. So if we draw a picture of cosine, that means the slope for sine at 0 is going to be +1, because that's the output for cosine at that point, okay? So that's an interesting fact about sine and cosine and why they're so closely related, is that the slopes are equal to its partner, okay? From here, the derivative with respect to x for tan of x is secant squared x. There are proofs for all of these. I'm not going to go through them because this video would be a few hours long. But again, you can look these up if you want to. However, for these, memorization might be the best key. But a nice thing is that sine and cosine are always together, and then tangent and secant are always together. All right, so these two will always share in the differentiations and later the integrations, okay? The derivative with respect to x for secant x is secant tangent. So again, tangent and secant are together, so that's going to be the result for this derivative here, okay? These are the co-functions. Anytime that you are differentiating a co-function, its derivative will be negative, okay? And again, that's due to the slopes and how they relate to one another, okay? So if we think about the derivative with respect to x for cosine x, that is going to be negative sine x, all right? So that's another pattern that you can see here. So again, cosine and sine are partners. However, when you differentiate the co-function, which is cosine, its derivative will be negative sine as opposed to the derivative of sine being cosine. And then some two new ones are going to be cotangent and cosecant. Now, just like tangent and secant, cotangent and cosecant are also together. However, their derivatives will be negative because they are co-functions, okay? So the derivative with respect to x for cotangent is negative cosecant squared. And then the derivative of x of cosecant x is going to be negative cosecant x cotangent x. So again, this is more about memorization, but remembering their pairs, that's going to make it easier. So sine and cosine, tangent and secant, and then cotangent and cosecant. All right, the last two are going to be the exponential function and natural log. So the derivative of x, the derivative with respect to x for e to the x is e to the x. And we talked about this a little bit in class when you were relating f prime on the chart from the ICA. This is saying that the slope at any point on this exponential function is the same as the output, okay? So if you have a slope, so at y equals 0, you're going to, not y equals 0, at x equals 0, e to the power of 0 is going to be 1. That means the output is 1, and the slope at that point is also 1. And this is true for the entire domain of e to the x. All right, lastly is our natural log. So I want to rewrite this a little bit. Let's say that we are taking the derivative with respect to x for natural log of u, such that u is a function. U is a function. All right, this means that when you differentiate this, you will end up with u prime over u. So the derivative of u divided by u itself. Okay, and this makes sense because if you try to use the power rule, think about the power rule. If we rewrite this, this is technically, think of, how did we get there? The derivative, natural log of x. Oh, that's for integration. Never mind. So we'll talk about that once we get to integration. I'm thinking of something completely different. Okay, so we'll end it with that. So if u is a function, let's rewrite it another way so that we can see. Let's say that u is f of x. So d of x, we're going to take the derivative with respect to x for natural log of f of x, okay? Now, this means we will have f of x in the denominator, and we will have f prime of x in the numerator. So technically, this is the chain rule at work again, okay? If you take the derivative of the outside, which is natural log, that's going to be 1 over f of x. And now the inner function, you want to take the derivative of that, you'll multiply by f prime of x, which is just f prime of x over f of x, or you can say u prime over u, okay? All right, so that is a long introduction of these rules, and we'll be using them throughout the unit. Hope this helps.